So the topic we are going to cover today is techniques to handle skewed datasets. This session is designed for people who are either beginning their journey in data science or are looking to strengthen their foundational understanding on how to train AI models. While working with real world data, we more often than not encounter skewed datasets. So to train AI models using such datasets, we need to incorporate multiple techniques in our training for the imbalance in the dataset. So in this webinar, we will explore what those techniques are and when to use them appropriately. So before we dive into this webinar, a brief introduction of myself. My name is Amar Asim. I'm a data engineer trainee at Data Science Dojo. I am currently pursuing my bachelor's degree in computer systems engineering from NED University, and I specialize in Python programming and Azure-based tools such as Synapse and Microsoft Fabric. So in this webinar, we will start by understanding what skewed datasets are. Then we will look into techniques to handle the skewness. Then there will be a Python demonstration. And finally, there will be a question answer session. So let's just dive in and start by understanding what skewed datasets are. So when we talk about skewed datasets, it's important to recognize that skewness can show up in many ways. But for the purpose of this webinar, we are focusing on two broad categories. Number one, class imbalance. And this happens when the target classes are not evenly represented. For example, a dataset with 90% of one class and 10% of another class. This is very common in real world scenarios like fraud detection or disease classification datasets, where one outcome is much rarer than the other. The next category is feature skewness, and this refers to asymmetry in the distribution of a feature. A feature is an input variable, and it is basically the x feature, and the x is the input variable, which is we refer to as feature, and its statistical distribution when it's asymmetric, that we call feature skewness. So let's start by understanding what class imbalance is. We will take an example of a small dataset of 10 balls, where 5 balls are orange balls and 5 are blue balls. In this case, we have a balanced dataset because both classes, orange and blue, are equally represented. This is what we call a symmetrical class distribution, where each class makes up 50% of the data. Since there is no dominant class, we say that this dataset has no skew or no class imbalance. Such datasets are ideal for most machine learning models because it ensures that the model does not favor one class over the other while prediction. So let's take another example. But in this example, there we have 8 balls which are orange and 2 balls which are blue. This time, the class distribution is unequal, meaning that the orange balls are much more frequent than the blue balls. This kind of dataset is known as a skewed or imbalanced dataset. The major challenge here is that the machine learning model might focus too much on the majority class and ignore the minority class, which leads to biased predictions. So, now that we have an understanding of what class imbalance is, we will take an example where we have a dataset of, we continue to our example with the 8 balls, orange balls, and 2 blue balls. But now we divide our dataset into a training and test dataset. Here we can observe that in the training dataset, we have no representation of the minority class. In such a case, our model will not learn to predict the minority class, which will lead us with only the majority class as the prediction result. In addition to this problem, there's also the possibility that in the training set, even though there is a representation of the minority class, but since the majority of the balls are orange, the model will be biased towards classifying them as orange. As a result, even if a ball is blue, it is likely to be misclassified due to its minority status. Let's now talk about skewness in the context of feature distributions rather than class labels. A feature or variable is said to be skewed when its distribution curve is not symmetrical. So here you might wonder, what is a distribution curve? A plot of frequency or probability in the density of different values the feature can take is called a distribution curve. So in this plot, we can see that in the middle, there is a symmetrical distribution, which is represented by a balanced bell-shaped curve, which shows that there is no skew. On the left-hand side, we can observe that the right tail is longer, meaning that more values are concentrated on the left. Such a distribution is said to be a positive skew. On the right-hand side, we see that the left tail is longer and more values are concentrated on the right. This is called a negative skew. Another interesting thing to note is that in a symmetrical distribution, we have equal values for mean, median, and mode. So recognizing this skewness is very important for us because many algorithms assume normally distributed data. So if the data is heavily skewed, it will affect the model's performance. Later on, we will look into techniques to handle such skewed features. With Now, we will go towards the problems caused by the feature skewness. So number one, there's poor model performance. So skewed features can dominate distance-based or linear models, leading to biased predictions. Next up, we have slow convergence, which simply means that the models may take longer to learn if input feature vary in scale due to skewness. Thirdly, we have violated assumptions. And by violated assumptions, we mean that most models assume normally distributed features, but since skewness breaks that, this violates our assumption. Next up, we have outlier sensitivity. Skewed features often contain extreme values with long tails that might mislead the model. So that is termed as outlier sensitivity. Finally, skewed features can distort the true relationship between a feature and a target. This might cause them to mislead the feature importance. So now that we have an understanding of what skewed features are and what class imbalance is, let's look at techniques to handle this such skewness. So the first technique we are going to discuss is transformation. Transformation is a broad category of techniques in which there are multiple subcategories. So transformation basically means that changing of the representation of features without changing the actual quantity of the features. This helps us learn despite imbalance. So here we are going to look at class weights adjustment and transformations using feature engineering like log transformation and square root transformation. So when we look at log transformation, we use it to mitigate feature skewness. And how we do that, the concept behind using log transformation to mitigate feature skewness is that skewness is more when variance is higher. By taking the log of our original values, we can reduce the variance of our values. This in turn will lead to lesser skewness. Like log transformation, square root transformation is also used to reduce feature skewness. And similarly to the concept of log transformation, reducing variance, square root transformation does the same thing. There are several other statistical transformations, such as box-Cox transformation or min-max scaling, that apply the same principles under different conditions to correct skewed feature distributions. Next up, we are going to look at class weighting. So class weighting adjusts the penalty of each class during model training. This is especially useful in imbalanced datasets where some classes are underrepresented. This prevents the model from ignoring minority classes, and it improves the recall and precision for rare classes. Another advantage of class weighting is that it avoids the need for resampling. The model penalizes the misclassifications of more important, which are in this case the minority classes, more heavily in the loss function, and this is done through assigning weights to our classes. The weight is often inversely proportional to the class frequency. So the key takeaways in class weighting is that class weighting is a smarter alternative to resampling when handling imbalanced datasets. It helps the model focus more on underrepresented classes without changing the data itself. By adjusting the loss function, it can lead to better performance on rare classes while keeping the training process efficient. This is ideal for cases where resampling might introduce noise or lead to overfitting. Here, we are going to continue with a previous example of 8 orange balls and 2 blue balls. In this case, we can assign weight to the majority class and the minority class, which will in turn allow the loss function to prioritize the minority class. So by giving minority class a higher weight, we can increase the penalty for misclassifying it, ensuring that the model pays more attention to the minority class. Next up, we are going to look at the series of resampling techniques, with the first one being oversampling. So oversampling is a technique which is used to balance imbalanced datasets by increasing the number of minority class samples. So this prevents the model bias towards the majority class and improves the recall and F1 score for the minority class. A major advantage of oversampling is that it keeps all the data intact. So continuing with our example, if we oversample this dataset, we can say that we can increase the number of minority class by adding 6 synthetic data points in our original 2 points. This way, we will have even representation of 8 balls each for both classes. However, there is a downside to this. Since we are adding synthetic data, this might affect the overall integrity of our dataset, and this might not be useful for us. Next up, we are looking at the counterpart of oversampling, which is undersampling. So undersampling is a technique used to handle imbalanced datasets by reducing the number of majority class samples to match the minority class. This creates a balanced dataset without adding any synthetic data. It also reduces the training time by shrinking the dataset size. However, there is a trade-off. Since by reducing the dataset size, our model may not be able to learn the patterns and will in turn not perform as well. So, if we take our previous example, in this case, we will reduce the number of orange balls from 8 to 2, which matches the number of the blue balls. So the key takeaways from undersampling are that undersampling offers a simple yet efficient way to balance class representation. and it is best suited when the dataset is large enough to handle the removal of majority samples. This also helps us reduce noise and overfitting from excessive majority data. While effective, it should be carefully used to avoid losing valuable information. Another interesting thing to note is that both oversampling and undersampling are not mutually exclusive, meaning both can be used together to get the desired results. Now, let's talk about stratified sampling. So, stratified sampling is a technique that ensures that each class is proportionally represented in any sample, and it is most commonly used during train test split. So, in this case, we are going to consider an example with 25 a dataset of 25 balls, where 20 balls are orange balls and 5 balls are blue balls. If we create a stratified split for this dataset, we can divide it into a training set and a test set. In the training set, we are going to use 20 balls, and in the test set, we are going to use 5 balls. This gives us an 80% orange distribution and 20% blue distribution. So, using the stratified split, we observe that in the training set, there are 16 orange balls and 4 blue balls, meaning there are 80% orange balls and 20% blue balls. This is the same proportion that we had in our original data set. Similarly, for test set, we have 4 orange balls and a single blue ball. This also follows the same proportion as the original data set. So, this ensures that 80-20 ratio is preserved in both subsets, and this is actually what makes stratified sampling unique. So, the key takeaways from stratified sampling are that it ensures that training and test sets maintain the original class distribution, and it does not alter the dataset. Instead, it splits the dataset while maintaining the class representation, making it ideal for consistency evaluations. Next, we are going to look at a hands-on Python demonstration. So, firstly, we are going to look at transformation strategies. So for the transformation strategies, I'm using the fair feature of the classic Titanic dataset from Kaggle. So let's simply import it from pandas and plot it using SMOTE. So once we plot the distribution of the fair feature, we notice that the tail end is on the right side and it is longer, meaning that this is a negatively skewed data. So in order to tackle this, we are going to use a series of transformations and compare them. The first step is log transformation. So log transformation is the most commonly used transformation, and it can be easily used from the NumPy library in Python. However, there is a limitation that the data should not have null values since and it should not have zero values. So after applying this transformation, we can replot our feature and we observe that the skewness has been decreased from 4 to around 0.5. This is a significant improvement. In next up, we are going to look at box-Cox transformation. The limitation of box-Cox transformation is the data must be positive and it can be imported from SciPy library in Python. Since the data we have in FAIR is not positive, so we cannot apply these functions. However, to have a gist of how this function is applied, let's convert the FAIR values to positive. So, after converting the values into positive and applying the box-Cox transform, we can observe that the skewness has been reduced. However, we cannot compare this to the log transformation as this data is heavily manipulated by converting it into a positive data. Next up, we have square root transform. This is not generally used as taking square root shortens the range of variables, but it can be used in some cases through the numpy square root function. So, after applying the square root transformation on our data, we can observe that it has to some extent reduced the skewness in our data, but it is not as effective as the log transformation. Similar to such transformation, there are many more transformations like min-max scaling, which can reduce the skewness of our data. Next up, we are going to look at the resampling strategies for imbalanced datasets. So for this purpose, I have used an imbalanced class dataset, and this dataset has class 0 as the majority class and class 1 as the minority class. So let's just forget that our dataset is skewed and try to train a model and see the results anyway. So for this case, I'm using an XGB classifier model. So from what we can observe is that we have got very good results as there is a 96.35% accuracy. However, this is just a hoax. Upon further evaluation, we can check the confusion matrix, which shows the correct and incorrect prediction for each class. In the first column, it indicates how many class zeros were predicted correctly, and in the second column, it shows that how many class zeros were predicted as 1. In the second row, it shows that all class 1 entries were erroneously predicted as zeros. So we can observe that in the first series, on the above side, we have the predicted class zeros, and on the x-axis, we have predicted, and on the y-axis, we have the expected results. So for class 0, we can observe that our model is very good at predicting that, but for class 1, there is only minimal correct predictions. So in such case, we can simply get a very good result by using class 0 with a simple print statement instead of training an AI model. So this does not work. So to counter this, we are going to use a series of resampling techniques. So to in the resampling techniques, we are simply going to balance out the classes by reducing the majority class or increasing the minority class. However, this might have some adverse effects on our data, so we must be careful while using this. So let's first try random undersampling. So in random undersampling, we reduce the number of majority class samples until they match the minority class samples. This means that now both class 0 and class 1 have equal class representation. Next up, we have random oversampling. In this random oversampling, we simply replicate our minority entries over and over until they match the number of samples of the majority class. This also shows that we are adding synthetic data in our dataset, but now the representation is balanced. So rather than using random undersampling and random oversampling manually, we can utilize the Imbalanced-Learn module in Python, which provides us with a series of sophisticated resampling techniques. And to do this, we can simply create a smaller dataset using the make classification method from the sklearn library. So in this dataset, we have around 100 entries, and the majority class is still the class 0 and the minority class is class 1. Now we are going to use a technique called principal component analysis to reduce the features of our dataset so that we can plot it easily. So we have plot our original dataset, and we can see that class 0 has the majority and class 1 has the minority. Now we are going to use random undersampling and random oversampling with Imbalanced-Learn. And to use the random undersampling, we can simply import the random undersampler and initialize it, and then fit it over our training data. So the Imbalanced-Learn library also offers us the feature to see that which samples has been dropped from the using the undersampling. And now that we can see that we have equal class representation for both the majority and the minority class, that is class 0 and class 1. Similar to random undersampler, we also have a random oversampler in the Imbalanced-Learn library, and we can resample our data simply using that. So this will replicate our points, random pick points, over and over until we have equal number of class representation. In this case, we have added 80 new random points. So apart from random oversampling, oversampling also offers much more techniques, with one being called SMOTE, which is called synthetic minority oversampling techniques. And this consists of synthesizing elements for the minority class based on those that already exist. So the working principle behind this is that it picks up a point from minority class and compute the k nearest neighbors for this point. So the k nearest neighbor is an algorithm in which we take k neighbors and conduct distance formula. So the closest k neighbors vote for the class of our new point. And in this case, that will be our synthetic point. So we are going to use the SMOTE from the Imbalanced-Learn library, and we can import it from the Imbalanced-Learn.oversampling. So we can simply plot this, and after plotting, we observe that our synthetic data has increased, and we have much more new points, and we can see that class 0 is represented by the blue dots, class 1 is represented by the orange dots, and our newly added synthetic samples are represented by the green dots. Next up, we are going to look at stratified sampling. So, stratified sampling is generally used in conjunction with cross-validation or train test splits. Here, we are going to use a technique called stratified k-folds. Here, folds typically refer to the subsets or splits of the datasets used during cross-validation. So the key takeaway from stratified sampling was that it will maintain the proportion of the data. So we will simply test this out using our dataset, And we can see that the original class ratio for our whole data set is 26.44%. Now we can manually inspect each of our fold to see that the training and test set have the same ratio. So for fold 1, we have 26.44% in the training set and 26.44% is working as expected. Similarly, we have a fold 2, a fold 3, and up to fold 5. So where this is used is if we want to check that how consistent our AI model is performing based on our training and test sets. So here's some recommended reading material. So you can look at the Imbalanced-Learn documentation and look at it also on GitHub. So now I'll be taking in any questions that you might have. So are there any questions? So I think the original dataset is right skewed dataset. Am I right? Okay, let's just check that. So are you talking about this dataset? The one in the Colab notebook? So if we take the dataset from the Colab notebook, when decision metrics and how can we know when should we use it? So the confusion matrix which you're referring to can be used when you have the possibility that you have skewed data. And essentially what confusion matrix does is it helps us better visualize the the precision and the recall of our data. Meaning precision basically means that the number of correct predictions for a particular class, and recall means that the number of predictions. So for precision, basically you can say the original Titanic dataset. Yeah, sure. Okay. So for the Titanic dataset, yes, we can see that we have the longer right tail, right? You can see from here. So the dataset is on the left and the tail is on the right. So I can maybe show you my slides. And what we have learned is that if the tail on the right is longer, it is a positive skew. So yeah, you are correct in that case. So the answer to that is, so does that answer your question? So you're correct, I guess. And so for the confusion matrix, we basically use it when we know that our dataset has an imbalance class, so that we can see the results that when or what of our class is being predicted correctly. So we can see from here that this is the original confusion matrix, and the visualization in the bottom is simply a heat map. So the confusion matrix basically shows us that what are the correct predictions of class 0, the predictions which are correct predictions of class 0, then what are the false prediction of class 0, then what are the false predictions uh, of class 1, and what are the correct predictions of class 1. So does that answer your question? Uh, I think who was so are there any more questions? Let me just take a look. So
We done
Shahtaj
with all of it? Yeah.
yeah.
Yeah, go ahead. What?
Yeah, so I was just wondering that what other questions there are, and if there are any. Okay, Shatar Nazim has said yes. So I guess that answers that question. Is
Yeah,
the
we have another
skew or
question in between.
bias?
Right.
Okay, there's another question. Is the skew or bias in the data ever considered important, such as the signal trend versus noise? Okay, so the bias of the data is always important. So basically, we studied that there are two, basically we have divided our class skewed datasets into two broad types. Both of these types can occur in a single dataset. One is class imbalance and the other is skewed features. So skewed features is caused by the increased variance in the feature, and that might cause, for example, outliers, right? And these outliers can cause bias in the data. So that's why we normalize our distribution so that it can becomes more predictable. So does that answer your question? Uh, yeah, outliers are a problem. So we must try to avoid outliers, and it is a necessary step in pre-processing to remove them. How can you visualize the entire difference between skewed data and treated or scaled data? So a good way to do that is using a distribution plot, and I believe Seaborn offers it with the name dist plot. So you can use that, or you can just use any um, bar plot or something which shows the distribution. So that may be helpful for you. What method to handle skewness do you recommend, and what factors should be considered to choose a method? Can we work with ratios too, normalizing them? Okay, so normalizing is basically termed as yeah, normalizing does work, but normalizing is not transformation. It is in normalizing, it does not directly affect the skewness, right? Since the proportions are kept constant. But when we transform the data, even though we can get original data back, we reduce the proportions or variances. So that's what helps us reduce the skewness of our data. So there's another question by Ruta Shah. How do you identify outliers and remove them easily? So the simple way to identify outliers is that you can simply compare them against their mean median mode, and that will be I think mean is the most common, but you can also do it with the median, and that can be a way to detect the outliers. Or you can simply check the feature distribution, and the tail end on the right and left side are the outliers. So if the tail end on one side is longer, you can conclude that there is an outlier on that side, either positive or negative side. So there's another question. So we will log transform. Okay, so there are a couple of limitations in each transformation technique. For example, in log transform, we cannot handle null values, or as you may know, that the answer of log 0 is infinity. So we cannot handle a zero value. So depending on your use case, you will either use log transform or square root transform or box cox transform or a min max scalar or any different transformation. But the idea behind each transformation is pretty similar, that you have to reduce the variance and in turn the skewness of your data set. So does that answer your question? Okay, great. So are there any more questions? Okay, there is another one. What are the best case scenarios when we should use oversampling or undersampling? Okay, that's a great question. And for oversampling, we use that when we cannot afford to reduce our data set further, much further, right? So as you know that all AI models are trained on large amounts of data, and if you don't have such large amount of data, and then I would recommend oversampling, as you cannot afford to lose your data, right? But if you have sufficient amount of data, I will always go towards undersampling. And both of these techniques can also be used in conjunction, but there is a downside to each of them. We have already discussed the downside of undersampling, but the downside of oversampling is that you're adding new data into your original data set, which is calculated data. That's not the true data. So that might not represent your real world problem, and it will affect the overall integrity of your data set. So we have to be very careful when we are using oversampling. So does that answer the question? So what is considered a large amount of data? How many records is considered large? So that also depends on the use case. So for some cases, maybe there's a million entries dataset, and maybe, and in some cases you have a dataset of 10,000 rows. So it all depends on the scale of what you're doing. But in a general rule of thumb, you should probably have at least more than 1,000 entries at the very least. So are there any more questions?
Guys, we do have some time as well, so feel free to ask any questions that you want to, and we'll be happy to answer them. Meanwhile, while you guys will be sharing any questions, I would like to showcase our conference that we have been working on. It's a big conference that is coming on May 27th and 28th. I hope you guys are able to see my screen. It's basically, we're thrilled to announce basically an exciting update, our virtual event, Future of Data and AI. Agentic AI is happening on May 27, 28, 2025. We have already confirmed an incredible lineup of speakers, including Bob Van Louis, CEO of Aviate, Jerry Liu, CEO of Llama Index, Louis Serrano, founder of Serrano Academy, and a lot of other top-notch speakers as well. This two-day virtual and free of cost event is packed with dynamic sessions, expert panels, and hands-on tutorial on agentic AI. You can register now, and I'm sure that you will have the link on the chat box as well. So don't forget to check out and register. It's a free of cost event, and it's a virtual two-day one. It will be filled with a lot of information. Moreover, feel free to go to join our Discord community server. We have all the exclusive resources shared here. We have a lot of top-notch experts that are added here to share the expertise. Moreover, our live webinars as well as the recordings are shared here, so you can stay up to date with our upcoming events as well as our recordings for the past webinar. This event will also be shared here, the recording, and will be RSVP'd to you after the session as well. So don't forget to join the community server as well. And now we will go back to the questions that we have. We still have a little time. If you guys have any questions, feel free to ask, or we'll sign off. So don't forget to check out our conference page for sure. It's a big event and it's going to take place on May 26th, 28th. It's going to be huge and it's free of cost. So I'm sure that you guys will have a lot of value from it. So if we don't have any questions, we'll wait for 2 minutes and then we'll say goodbye. And thank you, Amar, for truly an insightful talk. And I think we have a lot of questions. We had a lot of questions for the event. So I'm sure it was fruitful for all of the people who have joined and took time for the event. Feel free to join our upcoming events as well and share it amongst your network. Till then, see you guys in the next event. It was nice having you. And we have another question from Robbie. Amari, can you just answer that?
Right. So the question from Robbie is, what is goal to find the best prediction of expected value from the data? So the goal is to find the best predictions basically. But can you please elaborate on the question, Robbie? I'm not really trying. I'm Yeah, please elaborate the question. Thanks.
For sure, Trevor, you will get the confirmation and
How do you know your output is what you are looking for? Okay, that's a great question. So what we do is we divide our data set, original data set, which comes from a real world values, into two parts. One is a training set and other is a test set. So the training set is the majority of the data set, and we just take a small chunk of the data set out and leave it for a test set. We train our model on the training set, and then we use that to predict the test set. So for the test set, we have its original real values, and we can compare the predictions with its original values to determine whether our model is good or not. Does that answer your question?
if it does, we let us know if that only like answers your question and you're 100% clear.
So you have a success. So basically, the model I trained had a very high accuracy, but it was not a very good model because it was only predicting class 0 successfully and it was not predicting class 1 at all. So I gave an example that you can simply use a print statement with every output being class 0 and it will probably have a very good accuracy. But that's not what we want, right? So we have to be careful of these things. And that's why I suggested that we should probably take a look on the confusion matrix to see that what are the results of the minority class predictions as well. So that's what determines a successful model for us. So stratified is basically not the best solution. It is an alternative to resampling. So if we do not want to add or remove any data, what we can do is we can use its stratified sampling in conjunction with cross validation, and that can probably help us elevate some class imbalance issues, right? So there is no, I guess I can say there is no best solution, which there is no solution that fit all the problems. So you have to be very careful and use it from use case to use case. So does that answer your question? Can the transformation be reversible? Yes, the transformations are mostly reversible. Like when you look at log transformation, we have the thing called exponent or anti-log, which can give us the original results back. That's what makes it a transformation. We said transformation is the change of representation, but not the change of quantity. So that's why the transformation is reversible. So, but oversampling, undersampling is not reversible, right? Yes, you are correct in that assumption. But generally, when we are resampling the data, we always have our original data set with us somewhere else. So it's not really lost, right? So we can always just go back to our original data set.